Okay, so yeah, so today we're gonna continue to talk about real-time rendering. So I think I tried to give a little bit of a taste of what that means in the hybrid topics video last week, and uh, I think in particular we were. Let me go over here to the. Yeah, we were talking real-time rendering, what rasterization is, rendering pipelines. Anybody read the Lindholm paper? The user programmable Vertex engine. This is kind of neat. 2001, so this is essentially when the GeForce 3 was coming out from NVIDIA, and the whole idea is, hey, let's go ahead and make some of this programmable, because versus having a fixed function pipeline where you have a fixed, all the hardware and lighting is all predetermined what it's supposed to be, and what was happening is your APIs are starting to like balloon up, like because we want to add bump mapping, we want to add shadows, we want to add all this extra stuff, and then we're basically trying to support this huge like model with the software. So this was kind of one of the first things of like, okay, let's move away towards that. And let's kind of embrace RenderMan kind of idea where we just use shaders to kind of handle all this. So, yeah, this is good. This is a good paper. Kind of illustrates what this kind of looks like on hardware. So, I'm trying to put the papers that I'm expecting to use for the final and everything. So it's well worth your effort to read those. And I try to include time for, right, we have about an hour and a half. I try to include time for being able to do these different things. So, okay, let's see here. Any questions on the hybrid topics for last week?
I don't understand the Z values property, like how it is changing. So far we are trying to track the nearest point of the surface, but how it's actually like going on, like it detects the first one, like how it's changing actually the Z values.
For the Z buffer?
Yeah.
Oh, okay. So essentially, every time you're about to write a fragment in there, you read from the Z buffer, and then you compare. So, is my current Z value less than the one that's already in there? And then if it is, then we go ahead and draw that pixel. Okay. And if it's not, then we just throw it away, because it's obviously further away from the. It's further away from the position. So we can actually play around with that a little bit. So what I was thinking about doing today was we'll just code. We'll just kind of go through, see how this stuff works out, and I was even thinking, depending on how much we get through today, I was thinking about maybe even continuing some more on Thursday, just streaming more coding of, and kind of maybe focus a little bit on the homeworks. That way we can, we kind of got a little behind on the homeworks, but we're going to try and catch up. That way we kind of spend time actually doing this stuff. So, but today we're going to spend the time on real-time rendering, and then we will, Thursday we'll focus more back on the ray tracing, so we can kind of do the ray tracing stuff. And if you noticed on the homeworks that, I don't know if I put it in here or not. I think I was adding it to Chrome here. I tried to make the where is it? The homework's a little bit more flexible so that you can focus a little bit more on the final, I guess, the final output a little bit. So let's take a look at that. Let me edit that. Okay, so essentially, what I want you to do is use a path tracer to render a 3D scene, and then submit a one-page report, which basically includes a screenshot and how you generated the image. All right, so I'm kind of interested in seeing what we can make with the path tracer. So whether that's modifying what we already have as far as the examples go, or just using a separate one like Corona or another rendering. But we want to focus on, okay, what's the main difference? Another thing you could do is use Peter Shirley's ray tracing in one weekend book. So if you want to do C++, or so those are all good avenues. Okay, so let's hit submit. Make sure that, and then it seems like when you're streaming, the everything just gets slow. Okay, and then real-time render. So real-time render to create an active 3D scene, and then include a screenshot and a link to your program. So that's homework 2. So I tried to make homework 1 and homework 2 a little bit easier to catch up on, so it's not so much from scratch. So you can, and that way we kind of get down to the later ones. I may change homework 3 and homework 4. I just combine those. You only have this, so I'd rather have, I guess, 3 homeworks. So we'll probably, homework 3 will probably take the example code that we're working on now and do something with it. Okay, so first 2, find a path tracer. Homework 2, find a real-time renderer. It can be the one where the LibXor library we're using in class, and then homework 3 will be modify the real-time renderer and just to probably get rid of the homework, some of the extra homeworks, inundated with a bunch of homeworks. So does that sound good to everybody? Yeah? Heck yeah. And yeah, I'm not giving that one up. Yeah. Okay. In fact, I've been working on the LibXor library to do extra stuff. We're running the port so you can plug Xbox controller or something and use it. And then the sampler, I'm working on a sound effect library and a music library, so you can kind of add music and sound effects. The sampler is going to be anybody know what a sampler is? You know what a sampler is. What do you think a sampler does? It has to do with sound.
Similar, yeah, sampling.
Basically, a sampler just records a sound, and then you can just manipulate it. So, so like over here, I have the bass drum and the cowbell, but I do like a special effect where I'm just kind of like, let's just change the playback speed, and then you can add a filter to it, like a low pass filter or a high pass filter. Low pass filter is kind of neat because then if you add resonance to it, it kind of like makes this like sound. If you've heard like sci-fi effects, you probably heard it. So anyways, so like, I don't know if the sound is turned on in this. Let's see if it is. Okay. So all I did was just have it repeat. So you just take a sample, which like a cowbell or a bass drum, right? I just took a short one and just kind of changed the playback speed and added like some resonance to it. So as the filter is kind of going down, or as you're sweeping it, so you basically have like the waveform, right? So this is the maybe like a percussive thing has like a loud amplitude and then decays over time. Okay, and then you have the filter. So this is time and this is amplitude. So that's what the sound file looks like. And then this is the filter. And the idea here is that this is the frequency, and so normally like a low pass, so this is, like this would be like say 20 kilohertz, maybe this 20 hertz. So we're all familiar with that, I think. So low pass filter basically says, hey, anything, whatever this cutoff is, then start chopping off the high end. So it'd be like, I want to hear the bass sounds, or I only want to hear the treble if it's a high pass, but low pass is really popular. So when you add resonance to it, what happens is you get this like peak. And so what ends up happening is you really hear that particular frequency. So when you play it back, or you get this like, because that one frequency is like really like loud. So whatever is happening over here, whatever that frequency is, it's really loud. So we'll play with that for just a tiny bit. Just talk about the game competition. So if I minimize everything. We're going to load this. So sound synthesizers, like if you had a classic kind of sound synthesizer that could play triangle waves, square waves, just very basic kind of sounds, they kind of sound buzzy in a way. So like, I gotta set the audio settings here. Okay. I want a resize. Just going to make a very simple sound. So that's a sawtooth wave. So it sounds very buzzy. Okay. And then like square wave. Okay. Almost sounds like a video game kind of sound in a way. So, and this is sounds very buzzy, these particular kinds of sounds. And then triangle waves sound very, almost like one kind of tone. Okay, because there's more, it's very close to a sine wave. Not exactly, but it's very close. So what happens is, if you want to make that kind of sound a little bit more interesting, you can just change, the cutoff frequency. So that's kind of, I have it turned off way low, so we're only hearing like the low sounds coming through. I can turn it up. Okay, and so if I turn up the resonance, we're hearing that like one frequency kind of change. So what we can do is we can add envelope, which just changes it over time. All right, there we go. So over here, make that really slow, like 5 seconds. So it's like moving that frequency around. Yeah, it's really cool. Almost has this kind of frequency kind of self-oscillates, so you hear this like whistling sound as it's going through. But if you turn it down, then you don't really hear it as much. You just hear the sound kind of. So if I turn off that resonance, it's like you're turning the treble down and up and down on your stereo system. Which, if you kind of turn the cutoff a little bit down, then you kind of get these like horn kind of sounds. It's kind of interesting because we start with this like very buzzy sound, but by changing the way that the cutoff, it kind of sounds like somebody's playing a horn. Now that's kind of how these analog synthesizers kind of work. So anyways, there's this particular one that I really like because making sound effects can be difficult in the sense that, like, if you look at this particular synthesizer, there's like all these like knobs, and you're like, what in the world do all these knobs do? Okay, so it can be a little intimidating. I mean, I like the fact that you can mix them. So if let's turn that up. Is that? You can like mix them, and you can do all sorts of fun stuff. But that's not like if you're kind of new to making sound effects, and you just want to make like some really simple ones. There's this particular one that I really like called the Super Space Drum. And the Super Space Drum, it's by this company called Electro-Harmonix. So let me just kind of... They make another one called the Crash Pad, but it's this like little... the controls are like really, really simple. So let's look at the larger picture. So the idea here is you can set the start frequency and the stop frequency. So if you're just kind of trying to sweep something, and then you can say how long it should take to go from one frequency to the other. And then there's a way that you can add some modulation to it, although this is the part I really like. You just say, start here, stop here, this is how long it should take. Okay, and you can make some really crazy sounds. So I'll just play you a minute of this or so. I'm getting sidetracked because it's fun, but this is part of the game. I'm going to add some stuff to the library. So
in the late 70s, Electro-Harmonix developed and released a line of analog drum synthesizers. Over time, two particular drum synths from this era, the Crash Pad and Super Space Drum, have come to be favorites amongst modern musicians and vintage pedal.
It's kind of cool as you can make a lot of different kinds of sounds.
The Crash Pad creates drum sounds that are normally rich in harmonics, such as cymbals, snares, and hi-hats, by routing a noise source into a resonant filter, which can achieve self-oscillation. The Super Space Drum excels at kick and tom drums by sweeping its internal oscillator between the start and stop frequencies set by their respective knobs. A secondary oscillator can further modulate the Super Space Drum, creating otherworldly oscillation sweeps. In our first segment, we've connected 4 piezo drum triggers to crash pads and Super Space Drums, creating a playable electronic drum kit.
Yeah, they're cool. I'm just trying to like, because I figured that's the kind of sound you want to hear in a video game. It's just like.
Are those like hooked up devices?
What's that?
Are the pads hooked up devices? Like those.
Oh, I guess they use 2 vices just to hold the triggers for that. So yeah, so I'm trying to make the control simple. So anyways, I'm gonna, oops, I didn't mean to close completely out of that, but I'll show you. Where is it? Over here in the sampler. Essentially, so over here I just, oops, make that big so people can see it. So essentially I have it so that we can just load the sounds that we want. Everything's on a delay, it seems. So you can just load the sounds that you want. And then if you, let's see here. I'm still working on like the interface so that we can kind of, you know, see how long it should take. But because underneath the hood, so let me go to the source code. The web browser has this really detailed sound library that you can access. Where is the, oh, there it is. Audio, so over here. So you can do a lot of things, but it's not like, it's not designed, or it's not, I mean, it's designed to be powerful, but it's not like designed to be super easy to like do, because they want to give you a lot of things. So in this case, I just more or less want to set it up so you can just say, here's frequency 1, here's frequency 2, and then just go for it. And then there's a filter as well. So I'm actually working on a sample, on a system that you can just kind of like, okay, play this sample. So either you just have a pre-recorded sound effect you already want to use, or you want to do something like the more like a synth type, you know, where it kind of makes those 8-bit kind of sounds. So anyways, so that's coming. So we'll talk more about that, I think, in the coming weeks, just because we're kind of getting ready for this game competition. So a big fan of sounds and music. So I'm basically trying to add a library where we could say, okay, play this MP3 or this OGG file, and then load these sound effects, and then you can just kind of trigger them when they need to happen. Okay. All right, but today we're actually trying to talk about the real-time rendering stuff. So let's go ahead and get back on track. Okay, so real-time rendering, essentially, we have a bunch of models, just like we were talking the Reyes architecture, right? We have the models that we want to draw, and we're trying to get some kind of output, right? So, so today we want to use our library here to do that. Okay, so I've just copied a previous example, and I'm going to strip it out of some extra stuff. So first things first, I need to add that. Need to add our new example 15.html and the short description. We'll call it gbuffer. We're gonna spend our time working on gbuffer. And if you what did we define the gbuffer as? So that's the part where we could save the normals, positions, texture color, everything we might want to use so that we can do the lighting afterwards. All right. So we'll just draw that out here real quick. So normally what has to happen, right, you have your vertex shader. And over here, we're basically taking our 3D model we want to send it into the rasterization process. Okay. And normally what we have to do is we have to transform these coordinates. So we want to basically move from object space to projection space. Now, I'm skipping a few things in there, but what are the other spaces it's got to go through? World space. After world space, it's got to go into view space, right, for the camera. So we're basically have our because here's what's happening, right? Let's say we have the teapot model. We're going to bring in the teapot model. And this is the origin for this system. So we're basically saying, or I mean, the origin could be anywhere. Maybe it's on the bottom. It doesn't matter. So that basically says, okay, this vertex here and this vertex here, they're all defined relative to this position. Okay. So now, if we want to move our teapot in the world, right? Because right now everything's at the center of the system, right? At the center, but we don't want the teapot and every other object in the middle of the scene, right? That we want to move them around. Okay, so then we go, this is object space. Okay, then we need to go to world space. Now, what is the tool that we use to go from different spaces? Mathematical tool.
It was multiplying. It was multiplication or top.
It's a matrix.
Oh, sorry.
All right. All right. That's early. Okay. We use our matrix to go from one space to the other, right? That's so we have our world matrix. We multiply all of the coordinates of this, all the vertices, essentially multiply them all by the world matrix. And now we're in world space coordinates, okay? So, for example, just very simple, if we had a translation matrix, which is, okay, we'll just say tx, ty, tz. This is our translation, right? We want to move it to some other space, okay? Now, the way I like to think of it is that each column represents a very important piece, right? So this represents the x-axis, right? 1, 0, 0, that makes sense, okay? And this represents the y-axis of the system. So 0, 1, 0, that makes sense, right? And then this represents the z-axis. Okay, so we're going to columns here. And this last one is you can think of it as the origin to this whole system. Okay? Call that. That's how it's working, okay, in practical. Like the practical way that it's working. So this top 3 by 3 is a rotation matrix. So that basically says, so if I rotate the teapot, right, we're using cosines and sines to define how that's working, okay? And then over here, we have our translation, so this is where I want to move it. So if we have any position, we'll call it OX, OY, OZ, we're using homogeneous coordinates here because we can't have this O over here if we don't have that. So basically, we'd have to separate this as like a completely different arithmetic process if we don't use homogeneous coordinates. So this is technically W, and we can do some funny business later to get rid of it. But essentially, if we wanted to just move the teapot wherever we wanted, we can use this matrix. And just to show you that it works, we have right? 1 times OX plus 0 times OY plus 0 times OZ plus TX times 1. So you'll see that the first our first element up there, basically we just move the x coordinate by wherever this is located. Second thing, 0 times OX plus 1 times OY plus 0 times OZ plus TY times 1. And we end up getting OY plus TY. So the third one is just going to be OZ plus TZ. And this last one, 0 times OX plus 0 times OY plus 0 times OZ plus 1 times 1 is 1. So our W coordinate stays the same. All right. So just a refresher on what these matrices are doing, okay? Just so you can see in the flesh. Okay, so we have world space. I'm just going to erase this real quick. That's just a quick review. We'll take a look at it in the vertex shader again so we can see that. Okay, so we're going to world space. And then the next thing is we're going to eye space or view space. Okay, so this is the camera matrix. All right. Now, what is everybody familiar with the product of a matrix and an inverse matrix? What is that? What do you get?
It's inverse matrix.
If you have M and you multiply it by inverse, what do you get? Identity matrix. Okay. So this is important because this view space matrix is the inverse camera matrix. So if there was a matrix that said my camera is at this position, is pointing this one, this is the inverse camera matrix. So what effect would it have if we were trying to move the camera in the scene? We multiplied, let's say the object was the camera, and this was the camera matrix, and we multiplied by the inverse camera matrix, what's going to end up happening? You get the identity, but that has the effect of putting everything that the camera ends up being at the origin of the whole system, right? Because we basically just canceled those two out, so the camera is at the origin, okay? So what's kind of cool about the inverse matrix is that you basically can move one object into the space of another by multiplying by that secondary object's inverse matrix. So if we want to move everything in the scene relative to the camera, then we multiply everything in the scene by the inverse camera matrix. Okay, which is fun. Okay, so we have view space. So this is an inverse. Normally, this is your inverse camera matrix, and then the last step is the projection. Now, why is the projection matrix going to be important for us?
That's how we're going to map the pixels on screen.
You're pretty close. But what is projection?
To get the idea about the 3D, like the shape of it, like if we rotate it or.
Not quite. This is at some point over here. We're in 3D. We're in 3D. But we're trying to get to 2D because our screen is two-dimensional. We have pixels.
Yeah,
We would like faraway objects to look like they're getting smaller.
Yeah, I mean, get the idea about like what's the value in the x-axis and the y-axis from the specific point of the
Right.
content.
So what we're trying to do with the projection matrix is set this up so that, well, I guess what's the short answer of how do you do the projection? The short answer to that.
So like, if we think about a point on the object and then have the idea about the angle, like how it's aligned, and then with respect to the angle, calculate the cost of the item and sign up that it's advised.
It's actually a lot simpler than that. It's divide by z. So if we have x, y, z, and we want to go from 3D to 2D, then it's just divide by the z coordinate, depth, and that's how we get to 2 dimensions. It's really simple. Okay, so divide by z. So when we're doing projection, we're dividing by z. So sometimes we'll call it the perspective division. Okay. Now let's just kind of tie this into. Let's go ahead and tie this into. I'm just going to open up the. OpenGL pipeline.
So when we were talking about use case, it's kind of, I think you mentioned this in fundamentals, it's kind of similar to that feature on organic where how the spaceship moves isn't that the spaceship itself moves, but it moves the whole world around it.
That's right. So that's what this is all about, right? So over here we're saying move the teapot around in the world. And then over here, it's the effective way is just move all the objects around the camera. You're not really moving the camera, you're just moving all the objects around the camera to where they're supposed to be. That's a good way of describing that. And then this projection matrix is designed, because we're in homogeneous coordinates, x, y, z, w, and we kind of need to move away from the homogeneous coordinates into a way that we can do this division over here, okay? And the way that we essentially do that is, and I don't want to spend too much time on that, just really to know where that happens in the pipeline, but the perspective division is kind of geared so we can do this x over z, y over z, all right, but we have to do it in such a way that we put it into w, okay, so it's a little convoluted that way, but if we look at the if we look at one of the OpenGL specifications, it actually says all of this. Okay, so we can see over here that we normally have a model view matrix. So a lot of times, I guess the old way to do it, you just stick the view and the model in one matrix. Okay, I like to separate the two because we're trying to go to world space and then we're trying to do the camera space and then projection matrix. So once you kind of get through the, so you start with object coordinates, then you want to get to eye coordinates. Okay, so that's camera space. And then you have the projection matrix, so that's going to give us clip coordinates. And then we do the perspective division. All right, so once you get through the projection space, you're in clip coordinates. So we could take a look at that. So over here, there's our object x, y, z. So these are the vertices of say, the teapot. And we multiply it by the model view. And now this is where all those vertices are located in the space, in eye space. Okay, so then the second thing, and over here we can see essentially what we're doing. So we're going from object coordinates to eye coordinates, clip coordinates, then we do the perspective division. So then we get what's called normalized device coordinates. And then we need to do a viewport transformation. And the reason we do the viewport transformation is because essentially we're trying to get pixel coordinates, like where are we drawing this triangle on the screen. Okay, so here's the, let's go back here. So over here we have the projection matrix. So we multiply by the I coordinates, we get the clip coordinates, and then device coordinates. You see how we divide by W over here. So we're projecting from homogeneous coordinates down to device coordinates, but as you heard me say, we're actually dividing by Z. So I'll show you that matrix just a bit, but we are dividing by Z. That means that when we look at this projection matrix, we should see some evidence we're moving the Z coordinate into the W. All right, and we're actually doing this in such a way that the Z device coordinates are going to be what you throw into the Z buffer. Okay, so once you have these device coordinates, then you'll notice over here that we can set the window coordinates by essentially multiplying half the width of the viewport and adding the origin, so whatever the center is. Okay, this makes it so that you could have positive and negative y-axis and a negative and a positive x-axis. But maybe you want it different if you're doing a two-dimensional, like you want to draw to a certain pixel on the screen. You might have to set it up so the origin's actually at 0, 0. So you kind of move this around wherever you want. And you'll see over here that ZD is the, we're trying to also do Z and D so that it goes between 0 and 1. Okay, so that's the objective. Oops. This thing's moving around a bit. Okay, so the idea is we want X and Y eventually to be where we're drawing our polygon on the screen. We want Z to represent what we're going to render into the Z buffer. Okay, and so if we take a look at the matrix for let's go ahead and look. Let's look at glue perspective. If it doesn't work in this web browser, it'll work in the other one. Okay. Firefox. This is why you have to have 3 browsers. So, nothing works in one browser. Okay, so we'll let this load up. Okay, so normally we have like the field of view. So what's the angle that we're trying to look at this? What's the aspect ratio of the screen? What is our near and far supposed to be? So that's essentially what we want near what our 0 to 1 coordinates are going to be. Okay, so here's this matrix. So you remember I said that we were trying to move the Z coordinate into the W. So over here you'll see on the bottom that we have, if you could just imagine the X, Y, Z, W over here, you'll see that W is 0 times X plus Y, 0 times Y, minus 1 times Z, and 0 times W. So we basically move Z straight into the W, right? So now when we divide by W, what's going to happen? We get W over Z, Y over Z. That's what's going to happen there. So when you're trying to understand what the perspective division is all about, divide by Z. That's how you get your 3D perspective. Okay. Now over here, you'll see that we're that for X and Y, we're trying to match those because it's very rare that your frame buffer is every 1-to-1, right? I mean, movies are normally really wide, like almost like over 2-to-1 aspect ratio. If you go see a movie in the theater, like 2.2-to-1, that's the ratio. If you watch TV, old-fashioned TV is 4-to-3. So if you had an old-fashioned TV growing up, and then modern TV is 16:9. Okay, so this f value, right? So if you take the cotangent of the field of view divided by 2, that basically tells you, how much should you squish the y, okay? And then the aspect ratio is, you take 16:9, you divide that by 16:9, and you make sure that you have enough horizontal that doesn't look like it's all squashed. Okay, so now this last thing, as I mentioned, we're basically trying to map the z values from 0 to 1. And this is what does it. Okay, so we have far plus near over near minus far, and 2 times far times near. So if you multiply this, what's going to happen is that when you divide z, it's effectively going to have the, we're basically going to move it from 0 to 1. That's what we're going to do. So 1 represents far away, and 0 represents close by. Okay, so let's just say, just for that our near is a value, let's just say it's 1, and our far away value is like 100. Okay, so if you have this one over here, so we're going to have, so 100 plus 1 over 1 minus 100. So that value is going to be very close to, what, minus 1? It's going to be very close to minus 1. It's basically 101 divided by minus 99. So it's a value that's very close to 1. And this one over here is going to be 2 times 100 times 1. So that's 200 divided by 1 minus 100, so over negative 99. So this value is very close to what, minus 2 or so. Yeah, 200 divided by minus 99. Okay, so this value is like a number very close to minus 2. So we're going to have our z value over here is going to be whatever our existing z value is times this one minus that one. So let's just say that, I guess it'd be helpful to like look at that. So let's use my favorite tool here, or one of the many tools. Just throw this stuff in a spreadsheet so you can see what's happening. So we're going to open up Excel. And this is mostly just so we can convince ourselves that the math is going to work out. Okay, so we have z near, z far. Let's say that's 1, that's 100. Name these so that we can use. Okay, so if our z value, and we'll try some values, say like -1, then this is going to, let's look what our z clip is going to be. Or yeah, clip coordinates. So this is going to equal, let's go ahead and just, I'm going to calculate these elements here real quick. So this equals near, is it far minus near? Or far plus near? Far plus near divided by near minus far. Okay, and then that's 3, 3. And then we have 2 times z far times z near divided by z near minus z far. And that's the projection matrix, row 3, column 4. Okay. So now, if I'm going to multiply, we're basically saying it's that times this z coordinate plus W is always 1, right? So W is going to be, we're basically just going to add that number to it. Sure. Okay. So let's just see what happens over here. So we have that if our z coordinates are like -1, 0, 1, 2, 3. So as we're getting farther and farther away, our z coordinates are getting more and more negative. Okay, but if remember, we're sticking the negative z coordinate in W. So when we get the device coordinates, then it's this divided by that. So let's see what happens for device coordinates. Okay. This is why you never, ever, ever set your z near to 0, because then you're just going to get division by 0. So we don't do that. So just for sake of, just say, oh, this is interesting. As we're getting, this is sometimes where it's worth throwing these things in a spreadsheet and seeing what's actually happening. So if we have like -1, -0.1, -0.01, -0.01, we can see that as we're getting close to 0, right, that number is like spiking up. Okay, so probably once we have passed it, you'll see that our numbers are starting to kind of go down. Now, we should see something happen. Okay, yeah, so we have these, we have our z coordinates. So these are our normalized device coordinates because we have divided by z. So let's go back over to the to our specification, because we're trying to figure out how our z values are going between that range. So, oops. So we have one last, we want to get window coordinates. So now here's what we're going to do. Now we have to do this last calculation. Okay? So it's whatever our far minus near is supposed to be. And normally we set those to 0 and 1. Okay? So far is 1, near is 0. So this is going to be 1/2 times our device coordinate plus 1/2. Okay. So let's so we'll put window here, so equals 0.5 times that plus 0.5. Perfect. Okay. So, oh, maybe I was telling you backwards. Let's go ahead and jump up to 90, 91, 92, and let's go all the way to 100. Let's just see what happens after the... Okay, so you see over here that where our original z values, so aha, okay. So we have our original z values. So as we're getting further and further away, we're seeing something maybe a little bit unexpected. Okay, so, and this is something you have to kind of keep in mind, that when you're looking into the screen, you're looking not at positive z, you're looking at negative z. Now, did you realize that before I mentioned it? No. Okay. So, the reason why is because we're in a right-handed coordinate space, right? So if you want x to go positive and y to go like to our right, we want y to go positive going up, then right-handed, the z has to stick, positive z has to stick out of the screen. So that means Just do it over here. So we want that, okay? Because that's how we think about things when we're graphing something, okay? So if it's right-handed, z has to stick out. Positive z has to stick out. That means inside the screen is negative. All right? So why is it negative going into the screen? We can all say it together because we're using a right-handed coordinate system. Right-handed coordinate system. Okay? If you're using a left-handed coordinate system, what direction is z, positive z, going to point? In the screen. Positive z would point in the screen. Okay? So if you notice here, and this is why, like I said, it's helpful to calculate these things, just to kind of spend time to understand what's going on. So we can see over here that if our near is 1, well, why is it like not exactly, first of all, we're getting negative values, but 2, it's not exactly 1. Like we said, we're going to go from 0 to 1. Okay, so we're gonna reverse this order over here, and we're going to say we're going to go from positive 1, 0.1, 0.01, 0.001. And the only reason I'm doing this is just so we can see what happens when we okay, so -1, -2, -3, -4, -5, -10, -15, -90, -91. That should give me enough to keep going. Okay, perfect. So we can see that when we have set our z near value to 1, then when we're at z equal -1, then our z values, our window coordinate value is going to be 1. And we're all the way down at -100, then it's going to be 0. Something seems off to me. I think it's because we're multiplying this by -1. Am I doing... I think that might be it. There we go. Okay. Okay, so because we have this minus in the projection matrix, we have this -1 over here. When we go device coordinates, technically we're divided by -z. So then our -1 becomes 0. So anything near is 0. And anything far goes increasingly all the way down to 1. Now, let's, this is actually interesting because for the very simple fact that we need to kind of understand the nature of the z buffer a little bit. So I'm just going to delete these. So you can see over here that because it gets clamped, anything out of this range is going to get clipped off. Okay, we always want to clip. But this is kind of interesting that we might expect that because we're using linear values, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that the z buffer would respond in the same way. But you'll notice that it doesn't. And so let's graph that real quick. I'm going to create a scatter graph. And okay, so what does this mean? We have our z values, -1, -2, -3, -4. But what is this showing us? it's showing us that our depth buffer is not acting linearly. Okay, so we're not just like throwing. So there is like a sweet spot where, or if you set this near value too close to the basically to the clipping plane, right? The near clipping plane, you start losing the accuracy of the Z buffer very, very quickly. In other words, look how little. So this is what minus 100. So this is very far away, okay? And this is getting over here, so we're close by. So if you notice that, I guess about 20 or so, between like minus 10 and minus 20, we're starting to quickly like not have a whole lot of information. We're using most of the precision in the depth buffer to store values that are close by. That's what that means. Look how, in other words, by the time you get to about 10 units out, you only have like between 0.9 and 1. In other words, where most of the objects are in the scene, you don't have that much numbers left over to determine who's far and who's not. So if you set the Z value, the near value, too close, if you set it too close, then you will basically like zap up your depth buffer, and then it'll be harder to determine whether something is like close or not. All right. So this is something to keep in mind. You basically lose bits of information because the depth buffer normally have at least 16 bits of information. Okay, so that's what. Let's just say you can go 0 to 65, 535. That's 16 bits. So if you could imagine that, let's just type that in, like 0.9 times 65536. Actually, we want 0.1. That if just setting the Z value to 1 means that all the objects from minus 10 all the way to the far clipping plane, it's like we're saying we only have 65, they can be in one of 66,500 places. Whereas if the objects are close by, then they can be anywhere from like, almost 60,000. So you see that there's this function that relates how much, so if you set it too near, like let's play with that. If we set the Z near too far close, like 0.001, then look what happens. When you're like talking, look at 0.999, you have used so much of your available integers for things that are so close to the camera, it doesn't even matter. Okay, and so what ends up happening is that your objects that are getting further and further out have a difficult time like deciding whether they're close or not, because it's like the same value essentially. Okay, so word of wisdom: don't set this really any closer than you need to. Okay, so I think 1 is a good setting, like minimally speaking. Okay, so I used to do like 0.001 to 1000, which if you have a higher resolution frame buffer, like 24-bit, which is normal, or a floating point representation, then it's pretty good. But or you don't really notice it too much. But anytime you have like a lower resolution depth buffer, then it really shows. And that really shows like if you're trying to do things like shadow mapping or other things where you're relying on the depth of where you're relying on the depth buffer to kind of give you information, then then you have a difficult time telling whether things are shadowed or not, because the resolution, the way that this depth buffer works is it's front loaded. So anything close to the near clipping plane gets the accuracy. However, this allows, it's very fast for us to do it this way, because we have to do this projection anyways, this is the reason why we do this. Okay. Hopefully that answers all the questions on depth buffer. So then what we're going to do is once we've calculated these window coordinates, as we're writing them in there, then we basically say, okay, what's currently in there now? And we can have a function less than equal. We can actually set whatever function we want, but basically we just normally set it to less. So anything that's closer by the screen, then we can go ahead and just overdraw it, essentially. So the ideal case, 0 overdraw. You sort your objects front to back, and so you draw your nearby objects first, and then anything in the back just doesn't ever get a chance to get drawn. If you draw back to front, that's the least efficient way of doing it, because you basically spend all this time drawing objects that you eventually are just going to paint over. Okay, so that's kind of like the two things there. Okay, so we can see over here that we have this viewport transformation. So you can see that from the time we specify our object, our 3D model coordinates, to the time that they're actually getting drawn on the screen, they go through a bunch of math, essentially. Okay, and if we take a look at the, let's just say we went, was it basic.vert, you'll see over here that we are multiplying our projection matrix times our camera matrix, and then over here we have our world matrix times our position. So we basically go from object space to world space to camera space to projection space, and whatever we throw in GL position inside the vertex shader, then it goes through that separate process of let's divide by the W coordinate, and map it to where it's supposed to be in the window, and then it goes to the Z-buffer algorithm. Typically it goes to the Z-buffer algorithm first, I want to say, and then we draw the fragment. So any questions on that part of the process? Okay, so now we have that that done. We need to go ahead and add some models. So earlier we already played around with a rectangle. Everybody remember the rectangle object? Just basically we have a text file called rec.obj, and it's just got a rectangle from minus 0.1 to positive 0.1, just centered around the origin. Okay, and we got some texture coordinates. All right, which is really simple. So this is our so if we go here, that's what this is all about. So we basically are just applying it's the most basic thing you can do, but it's not the most interesting thing. We could at least do something a little bit better. So let's see how we could add a few different objects, and I'm gonna just go copy and paste some stuff. Z drive, UAF. I have a teapot model and a bunny model, a few other things. Courses, fundamentals. Okay, so a dragon model. I think I'll copy dragon too. Copy that one. Whoa. The bunny, box, a dragon, a geosphere. I normally do the Spones model too. The Mitsuba model, copy all sorts of stuff. Make GitHub not happy with us. Paste. Okay, so the idea here is that if we're doing, I guess if you're doing Windows, you can actually open these up. So if I loaded if I double click on the teapot model, I can just take a quick look at it. This is the Utah teapot that you've already seen before in several papers. And it's popular because Photoshop. Sorry, no, it's a waste of time. Gotta wait for Photoshop to load. I don't know why it's even associated with OBJ files.
Yeah, it's very strange. Can you load OBJ files into Photoshop?
I doubt it. I don't even hardly ever use Photoshop. I use GIMP, which takes just about as long to load. It loads fast in Linux for some reason. It doesn't load fast in Windows. It's something I wish they would fix. Okay. I meant to open this up with Paint 3D. So Paint 3D is like a Microsoft application that
So there's Paint 3D.
it's part of the. I think it is some kind of. I think it wants to render it. It's part of like the Windows Creators Edition update that they added a while back.
So does it allow texture painting and stuff on surfaces? Oh, yeah, that's not Blender's built into one.
Yeah, we can take a look at this too.
Because Blender has it's not very intuitive like the rest of Blender.
See if I can. Okay. All right, so while we're waiting for that to load, I want to go ahead and get rid of some stuff here. Display. Just a really short. Okay. almost a case of, can I get my teapot model to show up faster than the other one? Okay, so we're going to load the teapot, and I gotta get rid of this extra stuff. Save. Still loading. Gbuffer. So let's see if we can load the teapot here. It probably won't work. I have a feeling I know why, but oh, faster than I could do it in this other program. Okay, so we have working teapot. Okay, so that was step one, right? We have the teapot, and so let's just look at the source code that we did that with. So let me get rid of that. And I don't need any of those. We just kind of want the smallest. Okay, so we have our, so we're just loading the teapot. So inside the XOR, we have a property called meshes, and we can say, hey, load. We're going to call it teapot, and this is the URL that we're going to look for it at. And then inside the render function, then we can go ahead and say, okay, let's make our perspective matrix. We looked at that already. So we're saying 1 and 100, and our aspect ratio is 1 to 5, or it's like, sorry, 3 to 2. Right, so 3 over 2 is 1.5, and 45-degree angle. And over here we have an orbit camera, so we're just kind of like just getting a certain perspective on it. And then we're just rendering we're using basic.vert and basic.frag, but let's go ahead and because I don't want to mess up the basic.fragment one, so we're gonna make a copy of that. And this one we're going to call Gbuffer. So when we load up, get rid of this extra. So when we load up our shaders, now we're going to use this one. And so I said one of the first things we might want to do is draw the normals. Okay, so that's the first thing we're going to do. So let's draw vNormal. So now when this loads up, see if I can kill that so it's not sucking all our CPU away. All right. Okay, so this is our these are the normals for our model. You notice that it starts to go black over here. Okay, now sometimes it's useful because I asked the question on the hybrid topics. Well, what happens if you have negative values? You know, so what do we think happens to negative color values? Yeah, they're going to get clamped between 0 and 1. In other words, 1 is full intensity, 0 is the lowest intensity. So if it's negative, it's just going to get clamped between 0 and 1. So if we're trying to visualize normals, which might have negative directions, right? Then one way that we could do that is just to scale our values because it's normalized. Our x, y, and z will never be more than 1 or less than -1. So one thing I like to do when, say, visualizing normals is simply just multiply by half and add half. So we're going from -0.5 to +0.5, and then we offset it by half, so then that brings our values up to 0 and 1. Okay, so and then I could ask you the question is, why do we see the green? Why is green kind of showing up a lot, right, in this particular case? Green.
Oh, because the RGB,
because the Y value, because those normals are sticking mostly up. Okay. Now, if I'm correct, we're seeing some weirdness over here. So I have a feeling the depth buffer is not turned on. So let's take a look at that. Make sure the depth buffer is turned on. Aha, see, use depth test equal false. The default is true, so if we have the depth test turned on, then we should get, so if you're wondering why the Z buffer, right, is not working, so that part of the teapot's the other side, or actually that's this side, because Z represents the blue, right? So if it's facing toward us, we expect to see a lot more blue. And there we go. So so there's the Z buffer in action. So essentially, we're just kind of, if the Z buffer is turned off, we're just writing whatever comes in, and depending on if you're rotating the object, all of a sudden the backside might be a problem. Another thing that can happen is, and I'm gonna add a rotation here because we're almost out of time, but I want you to see this. Okay, so we're gonna do I want to add a rotation, so it's turning around, and let's do that. I want to say that that use cull face is the where's the render config? Well, maybe I don't have that turned on. Let me go down here. Okay, so another way of like helping to reduce overdraw is to not render back faces. Now, what does that mean, back faces?
of the outward faces of the inside of the mesh that faces on the inside of the mesh.
Right. Yeah. So this is a very important one to remember, and then we're done. So I'll let that when it decides to load.
That has to do with one.
Yeah. So let's say we have a triangle. This is vertex 1, vertex 2, vertex 3, right? And normally we do these counterclockwise. So we want it to be that way. And the reason why is because if we take V1 to V2 and V1 to V3, what direction is the cross product going to point in? This way, right? Okay, so our polygons are essentially two-sided. Okay, but if we have like, let's just say we have like a tetrahedron. These, if it's a convex shape, if it's not facing towards us, then that normal will be pointing away from the screen. And so it's a very easy test to see. You just check the normal, and if the z is positive or negative, you know that whole polygon is facing away. And if it's a convex shape, there's no point in drawing that triangle because you'll never see it. Okay, so backface culling is one way of helping to reduce overdraw by just not drawing triangles that don't point to the screen. Okay, so then we're treating them as one-sided. Okay, so over here we can, remember I turned off the depth buffer, and so we're seeing one side of the object, but as the object's rotating, you'll see that now we're getting overdraw for the other side. And so this is basically what happens if you don't have the Z buffer turned on. So we might be writing Z values, but we're not actually updating, we're not checking